So when you see STP, what that means is standard temperature and pressure. And when there's an adult talking at the front of the room, that means you should be quiet unless you have a question. Then you can raise your hand and ask a question. But when you see STP, that means standard temperature and pressure. It's a shortcut, meaning standard temperature, which is 0 Celsius, and standard pressure, which is 1 atmosphere. Now, the important thing, we talked about this before, but the important thing we have to realize is when we're talking about temperature in gases, we have to use the Kelvin scale. The Celsius scale is not what the universe uses. The universe uses the Kelvin scale. The Celsius scale is just a convenient number that we came up with. But in order to turn our Celsius into Kelvin, we have to add 273. So what these are all 0 Celsius, 0 Celsius, 0 Celsius, 0 Celsius. But we're going to convert it to Kelvin. Anytime you do any temperature math at all, you have to use Kelvin. So standard temperature is 273 Kelvin. Standard pressure is 1 atmosphere, whatever that atmosphere happens to be that you're using. 1 atmosphere, under 1,000 pascals, 760 millimeters of mercury, 14.7 psi, 30 inches of mercury, 764, 1 bar. I don't know why not atmosphere, sometimes bar. Just say, hey, let's make it a bar. Okay, so that's STP. So the typical exercise is a certain gas has this volume and this pressure and this temperature. What pressure does it occupy, or what volume does it occupy at STP? And you're like, it doesn't give me a number. Well, STP means 1 atmosphere, 273 Kelvin. Okay, so we did pressure conversions a whole bunch. I don't think we need to belabor that anymore. Avocado, this guy named Amadeo Avocado, for whom the number is named, he found kind of an interesting relationship. He realized that most gases behave pretty close to ideality. And when most gases behave pretty close to ideality, they all occupy the same pressure and volume for their number of moles. Which means 1 mole of chlorine gas occupies about the same volume that 1 mole of helium gas occupies. Which should make sense, because helium is very small, moving very fast. Chlorine is very big, moving very slow. Well, the fast-moving molecule can exert more pressure because it's banging into the walls faster. And the slow-moving molecule is moving slower but has more mass. So at the same temperature, they're going to behave the same. Just like with the kinetic energy thing. Remember the kinetic energy thing? 2 samples of gas at the same temperature have the same 1/2 mv squared. Well, this is basically an extension of that. And he found that since all gases behave pretty much the same, unless they're wacky non-idealities, then any gas at STP is going to occupy 22.4 liters. Kind of a neat little deal. I wrote it on this balloon, then I couldn't find a convenient place to put it. And see, it says 1 mole at STP is 22.4 liters. 1 mole at STP is 22.4 liters. This is about 22.4 liters. About 6 gallons is 22.4 liters. It's a molly balloon.
Oh, nice, man.
Okay.
Smack it.
Smack it? Okay.
Why can't we go back here?
I'll just put it right here for now.
Hit it 4 times.
Smack it later.
Smack it. Pop, 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 pop.
Stick it right there. Now Tony can't see the screen. No.
So just
It's
pull
all
it.
good, I can see it.
I'll just put it right here.
I'll hold it.
Yeah, I'll just set it right
Okay. Chris is
there. Okay, so does this make sense? It's kind of a fun little shortcut that should you have some gas at STP, 1 mole is going to be 22.4 liters. Just one of those things that they want you to remember. What I find more important is gas relationships. You take a hot air balloon, you fill it up with air. And then there's a burner, usually runs on a couple propane tanks, and you pull the burner and it goes, wah! Have you ever heard a hot air balloon? That's what they go. They go, wah! There's no exhaust, like, there's no exhaust pipe is just a big burner. Wah! And it heats up the air. And what does that cause the air in the balloon to do?
Expand.
Expand. And then it expands eventually to the point where the hot air balloon is less dense than the surrounding air, and the hot air balloon rises into the sky. So what happens when you heat gases? They expand. And this guy named Jacques Charlet realized not only do they expand in near perfect proportions, meaning double your heat, double your volume. Double your temperature, double your volume. Triple your temperature, triple your volume. So this is usually expressed two ways. One way is to express V over T equals a constant. You're going to find this online a lot. The other way is to express the way textbooks express it, and that is V1 over T1 equals V2 over T2. So Charlet found, we'll call him Charles because why not? So we call this Charles' law. Jacques Charles. Hey, Jacques. Jacques Charles found that if you hold pressure constant, volume and temperature are proportional. As one increases, the other increases proportionally. There's not even really a constant of proportionality. It's just V1 over T1 equals V2 over T2. Okay, questions? Give me a thumbs up if this is math you can do. You can manipulate these variables. All right, cool. So let's do some practice. Remember, temperature must be in Kelvin. So take a look at this first exercise. If a balloon holding 4.8 liters of gas at 21 degrees Celsius is cooled to negative 18 degrees Celsius, what will be the new volume? So using Charles' law, V1 over T1 equals V2 over T2, plug in the numbers and determine what our new volume would be. And once you get a number, ask yourself if it makes sense. The gas here is being cooled, temperature is going down, so you would expect the volume to go down. If temperature goes down, we expect volume to go down. Gases compress when they are cooled, expand when they are warmed. Tony, are you working or are you talking? V1 is 4.8, yes.
Would you or I do it by T1 or is that just a ratio?
Put the numbers into your formula and then use whatever math technique your math teacher is teaching you.
So how do we find T2? Because the temperatures are equivalent to 18. Plus 270.
Why? It's all changing. Normally when I make them, they're more symmetrical than that.
Make another one.
They're really hard to make, especially with the mustache. Because I have to blow in there and go, and then tie it off. And if I do it just right and I catch the mustache hairs and they're like, ah! And then they're like stuck in there. Yeah. Pull my hair out. Just trying to make this up. What temperature did you use for T1?
294.
294? 294 Kelvin. And what temperature did you use for T2?
255.
235?
255.
255? Now, what would have happened if you didn't convert this to Celsius?
You messed up like me.
Yes, you would have had a negative volume. You can't have a negative volume. So you got to use Kelvin. I made that negative for a very important reason. Okay, so once you get to this point, you can cross multiply or you can divide, multiply. You can just choose whichever math technique you like best. Either way, you get a volume. What's your new volume?
4.16 liters.
4.16 liters. Okay, then you ask yourself, when you have an answer that you like, you ask yourself, does this number make sense? The gas is being cooled, so you would expect the volume to contract. Did the volume contract?
Yes.
Yes, it did. Okay, shall we do another one?
Yes.
Okay, before I do another one, put your hand up and wave it around if you have a question. Good question. Celsius plus 273 gets you Kelvin. Okay, give me a thumbs up if you're ready for the next one. All right. A hydro balloon holding 15,000 liters of gas at 12 Celsius is heated to 85 Celsius. What is the new volume?
15,000 liters of gas. That's what I did. I didn't get a decimal. I got 204.49.
Hey, how many of you are going to the ACT prep tonight?
No, look.
Sports? Oh, I got tons. Okay. First period's like, we're all going to the ACT prep. You can't give us homework tonight. We have ACT prep tonight. Yeah, got lied to. Got hornswoggled.
So I did the right.
Oh, okay. They are mostly these guys in first period.
I would be going, but I have already promised to start it.
Yeah, I understand. You've got a lot to do. Those Pokemon aren't going to catch themselves. Those sports aren't going to build themselves. Those clans aren't going to clash themselves. You got responsibilities.
What is that other game that came out with? The beach rap.
Boom Beach?
Boom Beach.
Yeah.
Gosh, that game. Do you have 18,000?
I swear, if you said another word,
He would be, under the Geneva Convention, he would be well within his rights to smash those guys.
Do it!
Is 285 where we're starting?
Yeah.
And what are we ending with?
358.
358?
Yes, I know.
And this gives you a volume of how much?
66.2.
66?
I got 66. Wait.
1842? Okay. 18.1. 8,000 liters.
Oh, my bad. I divided by the wrong one.
Yeah. So again, guys, when you have an answer, your calculator is not smart. Your calculator is quite stupid, but it works very hard. So when it gives you an answer, ask yourself if the answer makes sense. The temperature went up, which assumes that, or which makes sense that volume would expand, and it did. Okay. Should we do one more, or we want to move on?
Hold on.
One more.
Uno mas. Okay. If a 3-liter sample of air at 41 degrees is heated until it has a volume of 4.2 liters, to what temperature was it heated? If a 3-liter sample of air at 41 degrees Celsius is heated until it has a volume of 4.2 liters, to what temperature was it heated?
I just got it. I got the right answer.
Oh, darn. I'm sorry, I'm not hearing that last. Okay. I swear to God, if you don't let me live my California dream, I swear. You know, please. You know,
Yeah, it does.
Okay, I take it from the chatter that you're ready to move on. What temperature did you use for T1? 314?
314 Kelvin.
314 Kelvin. And what temperature do you use for, or when you solve for it, what temperature do you get for T2?
439.6 Kelvin.
440 Kelvin?
39.
Okay. So let's ask ourselves, does this make sense? Our gas expanded. What causes gas to expand?
Temperature.
The increasing temperature. Okay. Give me a thumbs up. Okay, question. You can. Yeah. If you want to subtract 273 and turn it back into Celsius, that's fine. But in almost every case, you can just leave it in Kelvin. Okay. Now, I have a question for you. If I have a sample of water, which is at room temperature, 24 degrees Celsius, let's just make it really easy, 25 degrees Celsius. If this water is at 25 degrees Celsius, what temperature would it be if it had twice as much heat? If it had twice as much kinetic energy, what temperature would it be? If your answer was 50, it doesn't mean you're stupid, it just means you're wrong. Because remember, the kinetic energy, the universe doesn't use Celsius. The universe uses Kelvin. So 25 degrees is just a number that we came up with. What does the universe see when we see 25 degrees? What does the universe see? 298. The universe sees 298. When we see 25 degrees, the universe sees 298. So 50 degrees Celsius is not twice as much heat or twice as much kinetic energy. So to do this, you take your 25 degrees, add your 273, and you get 298 Kelvin. Take your 298 and double that, that's twice the kinetic energy. 596 Kelvin. So that's twice as hot. And if you want to know what it is in Celsius, take 596, subtract 273, and you're left with 323? 323 degrees Celsius. So what's the temperature of something that's twice as hot as 25 degrees Celsius? 323 Celsius. Does this make sense? This is important. It's important to realize that Celsius is, we have to think the way the universe thinks. Celsius is something we came up with. Kelvin is what the universe uses. Okay. Next, we talked about what happens when gas is heated. What happens when gas is compressed? So I got a sample of gas here. If I exert additional pressure, what's the gas going to do? It's going to squish. And if I reduce the pressure, what's the gas going to do? It's going to expand. And it turns out that this guy named Robert Boyle said, hey Charles, check this out. Just like volume and temperature move proportionally, pressure and volume move inversely proportionally. So there's a perfect inverse proportion between pressure and volume. In other words, when pressure goes up, volume goes down proportionally. Doubling the pressure halves the volume. Tripling the pressure thirds the volume. So you see this written as PV equals a constant, or as the way it's written in textbooks, P1 V1 equals P2 V2. That's Boyle's law. So it's kind of neat. By the way, we call this an inverse proportion. Just to remind ourselves the lingo, when one thing goes up and another thing goes up, we call it a direct proportion. When one thing goes up, the other thing goes down, we do not call it an indirect proportion. We call it an inverse proportion. Remember? Okay, good. Could save your life someday. Or at the very least, get you a couple points on the ACT. Okay, so let's do Boyle's law practice. Consider this. A bicycle tire has a volume of 8.2 liters at 4.3 atmospheres. What is the volume when the pressure is increased to 6.1 atmospheres? The gas was increased in pressure, so we would expect the volume to increase. You're early.
A little bit,
You're kind of
That's it. I just have to give it.
Give it to him. Yes? Nope, works in any pressure unit. Yeah. Good question. Temperature always has to be in Kelvin, but volume and pressure units can be in anything. It could be in pascals, atmospheres, torr, whatever. It's just, for simplicity, I like to leave the calculations in atmospheres. When you, if you choose to take chemistry AP next year, then they'll require you to use all the rest of the pressure units interchangeably, which is why you need to be able to convert between the two of them. But for exercises, I like to use atmospheres. So pressure of 4.3 atmospheres and a volume of 8.2 liters. And now we want to know what the new volume is when the pressure is 6.1 atmospheres times V2. Hopefully, because the gas was under higher pressure, the volume, if the pressure went up, the volume should go down. What did you get?
5.78.
5.78?
Liters.
How about 5.8 liters?
No,
Okay.
sorry.
Are we good here?
Yes.
Okay. Should we do another one?
Yeah. Are you looking for this?
Another one. Not really. If a helium balloon has a volume of 18 liters and 1.2 atmospheres, what pressure must it be under to expand to 2.3 liters, or sorry, 23 liters? Atmosphere.
I meant to say that it's 18 central.
What is 18? What's the number? What is that number?
What is the significance of 18? Who came up with all these numbers? There's so many of them. How can anybody keep track with all these numbers?
I just want to know what our number is.
Staff is there.
It's the
My favorite line from Beavis and Butthead before you were born was, "I'm angry at numbers. There's too many."
No, not just like my kids.
Exactly.
Okay.
Our volume went up, so the gas was allowed to expand. That would seem to infer that the pressure should go down. What's the new pressure?
0.939.
0.93 atmospheres. Okay. Seems like you guys got a pretty good handle on this.
Yes, I do.
Okay, give me a thumbs up if you're ready to